Ladies and gentlemen, hello. I am very pleased to present to you my work, Assessment of Mode 1 Stress Intensity Factors of Scent Specimens based on Digital Image Correlation Method DIC, case of ABS material, which is, for me, a worthy challenge and a great pleasure. In this perspective, I will present the work according to the following plan. I will start with an introduction, and then give an overview of methods and materials. Afterwards, results and experimental and analytic, and finally, a conclusion. We will begin by discussing some of the problems we will face, such as defects, deformation, corrosion, and temperature. Because of their severe operational conditions, many industrial components are subject to complex combinations of mechanical constraints. These combinations are at the origin of initiation and propagation of cracks in these parts, which contributes to the ruin of the structure, which is the aim of our work. Various analytical methods are used to study the fields of displacements, strains, and stresses in the vicinity of a crack. DIC is a well-established technique for stress analysis, and it has a wide range of industrial and research applications. Polymers play an important role in material science as a candidate for future new industrial materials, primarily because their properties can be tuned very easily. The flexibility of tuning polymers' properties comes from the number of available degrees of freedom, choice of monomers, branching, toxicity, copolymers, blends, and composites. The particular polymer studied here, ABS, the choice of this material is due to the diversified uses of it, the risk related to the used ABS structure in the industrial field, and the necessity to assess the crack and failure in a quick and simplified way. In fact, ABS has many deformation mechanisms like shear bands, striction, plasticity, threshold, and cracks. As shown in the curve of a tensile test polymer material, we can see different steps of deformation before rupture. Once the elastic zone is exceeded, the fibrils bridging the many cracks break because of the micro voids that are born around the defect. Consequently, the tenacity of the specimen decreases until the total rupture. I will now give a brief explanation of stress field around damaged structures. Fracture mechanics. Zone 1, crack initiation. Zone 2, early stage of crack propagation. Zone 3, later stage of crack propagation. Modes of fracture refers to the decomposition of crack tip stresses into three loadings or modes. The modes are Mode 1, stress orthogonal to local plane of the crack surface. Mode 2, stress parallel to the crack surface but orthogonal to the crack front. And Mode 3, stress parallel to the crack surface and to the crack front. In this work, we will study the Mode 1. In this mode, which the crack is stressed in tension, we use the relationships as shown in the above slide to define the critical stress intensity factor. Slide number 7. The particular polymer studied here is ABS, a common material for commercial goods. Indeed, ABS is a family of thermoplastics that contains three monomeric units, acrylonitrile, butadiene, and styrene. Typically, a styrene-acrylonitrile copolymer matrix contains discrete butadiene-based elastomer particles for toughening. Elastomer particles are grafted with sand to achieve necessary interaction with the matrix polymer. ABS is one of the most important rubber-toughened thermoplastics and is widely used for applications where toughness and surface gloss are important. The choice of ABS material is due to the diversified uses of ABS, the risk related to the use ABS structure in the industrial field, and the necessity to assess the crack and failure in a quick and simplified way. Methods and materials. We will now look at the experimental setup. To do this, we let experimental tests over standard specimen and set specimen for tensile test. The presented images below show the test bench and the specimens for a tensile test in order to characterize the material and study the behavior of the cracked specimen. The DIC technique was introduced in the 1980s. Since then, the quality of digital images has improved enormously, and multiple major modifications of algorithms have been implemented. Nowadays, the DIC method with high sensitivity and accuracy is utilized for testing specimens and, most recently, the whole structures. It can be used in a laboratory or outdoor environments. The DIC techniques are applied not only in the field of engineering, but also in medicine, mining, conservation of cultural heritage, etc. The experimental setup, as explained in the following slide, consists of sufficient light source, a high-resolution camera, a computer and frame-grabbing circuit card to digitize the output concept. The concept consists that the digital camera takes a picture of the surface of the specimen. Image is downloaded from the camera to a frame-grabbing circuit card. Digital image correlation method. The measurement of displacement deformation using the DIC system requires the following consecutive stages: preparation of the surface of the analyzed specimen, patterning, calibration of a device according to the required procedure using the DIC system calibration, recording images of the examined object material surface before and during its movement deformation, image analysis evaluation using a specialized computer program software, visualization of the results. Now we will present the results. To determine the mechanical characteristic, we cut specimens from a rectangular samples of ABS as shown in the table. We obtained a yield modulus equal to 1.25 GPa, yield stress MPa 28, maximal stress MPa 37,7, rupture elongation 8.2%. To identify the influence of the strain rate on crack propagation velocity, we carried out a series of tensile tests on our samples with different speed loading as shown in the following figure. The aim of this study is to measure the crack length in function of time by using a digital image correlation method. We can see at the figure the evolution of the crack according to the time for the different crosshead speeds. Firstly, we can notice that the crack spreads in a stable way, then it accelerates exponentially and thus causes a sudden rupture of the specimen. The ABS is approaching a completely fragile behavior at high speeds. Indeed, when the loading speed is high, the surface of crays quickly move away, which justifies the sudden rupture of the ABS. The macromolecular chains do not have enough time to reorient themselves within the crays. Thus, the fibrils bridging the many cracks break because of the microvoids that are born around the defect, which results in a decrease of the tenacity of the ABS. Whereas a sample subjected to low loading speed does not break rapidly, it slowly deforms under the action of mechanical energy provided by the external stresses and the thermal energy due to the molecular motions. Fibrils act as energy absorbers. It can thus be concluded that the rate of loading is a parameter that controls and influences the behavior of amorphous polymers. Depending on the loading speed, the ABS adopts either a ductile or fragile behavior. We will now look at the results of the digital image correlation. The following figure represents the displacement and stress fields obtained by the DIC method. As we can see, the high concentration of stress is located in the notch root. In this slide, we will present the formulas for calculating analytical and DIC stress intensity factor. In general, There are two methods for estimating analytical stress intensity factors, in particular, the extrapolation method near the crack tip and the method that uses the energy released during the crack propagation. In this study, we use the method of extrapolation of displacement fields at the crack tip. The stress intensity factor is related to the mode 1 displacement fields by the presented equation. The formula based on the mechanics of linear elastic failure for the stress intensity factor for cent geometry is given by F as a correction factor depends on the geometry of the structure. In our case, this factor is expressed in the following calculation. When calculating stress intensity based on DIC, we will use the following equation. In this slide, we will look at the curve of stress intensity factor in correlation to crack length. It can be seen that the propagation of crack occurs in three stages. The first stage corresponds to the initiation of the crack where it is stable. Then it evolves in a progressive manner, which is shown in the second stage, while the last stage corresponds to the sudden propagation which leads to the failure of the specimen. From the following graph, we can determine that the stress intensity factor based on DIC shares a similar result to that of the results of the analytical method. In conclusion, we will summarize our results in 2 points. The first one is evaluate a speed loading effect on crack growth. As we can see in the work, the ABS adopts either a ductile or fragile behavior. In the second part, we calculated the stress intensity factor using analytical and DIC method. We then validated the digital image correlation as a method which can be very useful in complex geometries where the relationship for calculating the stress intensity factor are not available in the literature.